My name is Suleman Aijaz. The topic of my presentation is gradient and RF spoiling. These are the contents. I'll start with overview, brief introduction to spoiling, and then the three methods that I've implemented: long tier spoiling, gradient spoiling, and RF spoiling. And I'll conclude my presentation with comparison. As we all know that protons are excited by applying an RF pulse, and after applying sufficient number of pulses, our magnetization reaches a steady state. Now, sequences are classified by the response of the transverse magnetization. Either they are called spoiled, either you will find them steady state free precession sequences. In a spoiled sequences, the transverse magnetization before each excitation is zero. It's completely spoiled. And in SSFP sequences, the transverse magnetization is not equal to zero before any excitation. So spoiling ensures zero transverse magnetization before each excitation, and in my presentation I'll only talk about the spoiled sequences. The significance of this spoiling can be seen from this image here on the bottom corner. The image on the left does not image on the left has the gradient spoiling, and image on the right does not have any gradient spoiling, and you can clearly see that image on the right lacks the quality in contrast. You cannot distinguish between the white matter and gray matter because it disrupts the contrast. It is quite difficult to achieve an image with a specific contrast because of an unwanted spin echoes are generated. Now, we can understand it better by analyzing spin echo sequence. Now, what happens in a spin echo sequence? We apply 90-degree excitation, protons starts dephasing after that, and after some time we apply a refocusing pulse of 180 degree, which rephases the protons, and at time TE we get the echo. Similarly, in non-ideal cases in other sequences, there can be a residual transverse magnetization, let's say due to small TR time maybe, which can generate unwanted spin echo, and it will degrade the contrast of an image. So we use a spoiling to make sure that that doesn't happen. Now there are three methods that I have implemented. First is long tier spoiling, in which, as the name suggests, you use prolonged repetition times of the excitation pulses. And the second is gradient spoiling. In gradient spoiling, at the end of the sequence you apply Z gradient. Now spins are already dephased, and applying the Z gradient introduces the random phase that averages the signal in the transverse plane, giving a zero transverse signal at steady state. Third method that I've implemented is RF spoiling. It again works on the averaging principle, but in this case, each excitation that we do in the transverse plane has some RF phase already with it. So in the end, all the RF phases, all the random excitations that we do will generate the average signal of zero in the transverse plane. Now I'll start with this long tier spoiling. Easy to implement, easy to analyze. MZ recovers completely. And as you can see here, after TR is long enough that our transverse magnetization decays to zero. It's the only problem with this is it's time consuming, and you do not want the patient to be inside the scanner for that long. In fast imaging sequences, TR gets comparable to T2, and it gets smaller, like 100 milliseconds or 10 milliseconds. Now this is the TR simulation, small TR simulation. What happens is when you reduce the TR, here TR is 100 milliseconds, 10 times smaller than what we had in long TR simulation. You can see that transverse magnetization here doesn't go back to zero. Now I would like to show you this derivation that we already did and we have already seen. Here we have derived the steady state magnetization by assuming that before the excitation, the steady state only composes of Z component. We assume that it is spoiled and there is no transverse magnetization. So the signal equation that we have derived only consists of the Z component at the steady state. But in this case, in small TR simulation, you can see there is no perfect decay of transverse magnetization, so this equation is no longer valid. Now from this equation, two things can be observed. One, the contrast of the image, the T1 weighting of the image depends on TR, the repetition time, and alpha. The parameter that we are interested in is TR, If you reduce the TR, you would get pure T1 weighted image. But in this case, since transverse magnetization does not go back to 0, you won't get exactly pure T1 weighted image. You would get something mixed contrast image. Now what we do is we forcefully disrupt the gradient, and by disrupting the gradient I mean by spoiling the gradient, and you can achieve it by using either gradient spoiling or RF spoiling. In gradient spoiling, before each excitation you apply the gradient. Just to keep one thing in mind here, signal is not eliminated at the end of TR. You can never achieve perfect spoiling by any technique. You would improve the contrast of an image but not spoil the transverse magnetization completely. This is the gradient spoiling that I have implemented. What here I disrupt the transverse magnetization forcefully by averaging the signal over 500 spins. Here again the TR is 100 milliseconds. The transverse component you can see here in the simulation, it goes to 0. I give it 5 milliseconds of time before the repetition time to degrade the transverse magnetization, and it reaches close to 0, but it's not 0 but small enough that it won't degrade the contrast of T1 weighted image. Now this is RF spoiling. The RF spoiling is trickier of all three spoiling techniques that we use. In RF spoiling we use this incremental quadratic recursive formula given over here, and the phi naught factor that is recommended in most of the papers is 117. So in RF spoiling what you do is you are exciting the pulses in the transverse plane with different phases. So you are already randomizing your excitations. So the purpose of RF spoiling is to achieve pure T1 contrast image. But in my simulation, perfect spoiling is not achieved because the randomness of the excitations was not enough to bring the transverse magnetization component to 0. Now this is the comparison. There is a trade-off between time, contrast, SNR, and the signal quality. Now if you want if time is not a problem, you can go with long TR spoiling, and you can give enough time for the magnetization to decay to 0. It cancels the transverse magnetization perfectly, gives you T2 contrast image, and SNR is high as well. But if you do not want the patient to be inside the scanner for long, you would either go for RF spoiling or gradient spoiling. Now most of the companies prefer RF spoiling over gradient spoiling. The one major reason is RF spoiling does not generate eddy currents. While applying the gradient, you are generating the eddy currents which can affect patient but in RF spoiling you do not have any eddy currents, and it is not spatially variant like gradient spoiling. Thank you.